So it's time to start. The next speaker is Professor Liutang Xue. The title of his talk is Revisit the Patch Problems of 2D Boussinesq System and 2D Incompressible Navier-Stokes System. So please.
Okay, thanks very much for the introduction, and also thanks very much for the invitation. It's a great honor for me to give a talk here. My title is Revisit the Patch Problem of 2D Boussinesq System and 2D Inhomogeneous Navier-Stokes System. First, I want to introduce the very famous vorticity patch problem of 2D Euler equations. Here is the 2D Euler equations in the vorticity form. It's a transport equation. Here U is the velocity field, and omega is the vorticity field. And U and omega is connected with the Biot-Savart law. For the 2D Euler equations, the global regularity of smooth solutions have been known since the 1930s. And Udwig in 1960s proved a very famous result that if W0 omega 0 belong to L1 cap L infinity, then there exists a global solution to the 2D Euler equations. And the particle trajectory xt will belong to this Hölder space. The Hölder regularity index will be decreasing as the time evolves, where the xt satisfies this equation. If we consider the omega 0 is a characteristic function of D0, where D0 is a simply connected bounded domain, then the Udwig result tells us it's global well posed. And the omega t can be expressed, it is still a characteristic function, and dt equals xt d0. It is evolved by the particle trajectory. The vorticity patch problem is the following. Whether the initial regularity of the patch boundary persists globally in time. For example, if the initial boundary belongs to ck gamma, whether the partial dt belongs to ck gamma for all time. Since the particle trajectory is not very regular, so it's not clear at the beginning. The vorticity patch problem was initiated in 1980s in studying the creation of small scales, and the numerical simulations once suggested the possibility of finite time singularity. That is, for example, the numerical simulation suggests the boundary will have infinite lengths, or the boundary will have some corners or cusps. However, Sherman, in several papers, proved that the global persistence result of ck gamma boundary regularity by using the paradifferential calculus and the stratified regularity method. The stratified means the conormal or tangential. Also that is the tangential regularity, the boundary that has much better tangential regularity. A simpler proof of the same result was later abetted by Bertozzi and Constantin. And they applying the harmonic analysis techniques and contour dynamic approach. For other proof, one can see Sarfati's paper. And also for the 3D Euler equations, the Vorticity problem, one can see the Gablin and Son-Raymond result. Now, for the inhomogeneous Navier-Stokes equations, this is the equation. Here, rho is the density, the u is the velocity. The first equation expresses the conservation of mass, and the second equation expresses the conservation of momentum. This equation models the incompressible fluid with variable densities. There are many mathematical research on this model, but I here didn't mention. I here only focus on the some noticeable results on related to the density patch problem. The Pierre Lyons in his monograph proposed the density patch problem. Let 0, be of patch structure, whether the regularity of patch boundary can be preserved. For the 2D INS system with rho 0 be such a patch, here at 1, at 2 are constant, strictly larger than 0. Liao and Ping Zhang in a paper proved that for initial boundary belong to WKP, K is larger than or equal to 3, P belong to 2 and 4, and the first 4 at 1 at 2 is very close. And then in another paper, they consider for any at 1 at 2 larger 0, then the evolved boundary, the boundary of the evolved domain will also belong to WKP. They mainly use they also use the stratified estimates of Sherman. And Dashun and Zhang and Xin Zhang in a paper, they consider the initial boundary belong to C1 gamma, and at 1 at 2 is very close. Then the C1 gamma regularity will be preserved. Gansendo and Garcia in a paper, they proved the C1 gamma, W2 infinity, C2 gamma regularity will be preserved, and also for any at 1 at 2 large 0. For 2D INS system with rho 0 just be the characteristic function of D0. That is, it's just a domain. Here is 1. The outside it is 0. Dashun and Muha in a paper, they considered the C1 gamma initial boundary. Here the D0 is belong to the torus. Then the C1 gamma regularity will be preserved. Now we turn to the Boussinesq system. The The viscous Boussinesq system without the hot diffusion is the following. Here, Cit is means the temperature. The U is velocity field. Here, Cit satisfies a transport equation, and in the equation of velocity, the theta ed as a forcing term. This equation is widely used in modeling the convection phenomena in the ocean and atmospheric dynamics. It also plays an important role in studying Rayleigh-Bénard's problem. Mathematically, Boussinesq system contains incompressible Navier-Stokes and Euler equation as special cases, since if Cit equals 0, it will reduce to the Navier-Stokes and Euler. And 2D inviscid Boussinesq system is analogous to 3D axisymmetric Euler system away from axis. We here also consider the temperature patch problem for Boussinesq system. That is, Cit0 is a characteristic of D0. D0 is a simply connected bounded domain. Then, since Cit satisfies a transport equation, Cit xt equals is also a characteristic function of dt. The temperature patch problem asks whether the initial regularity of patch boundary persists global in time. Daxun and Xinzhang firstly proved the global well-Boussinesq with Cit0 belong to this Bezier space, which admits the C1 gamma temperature patch data. And then in 2D as well as in 3D under a Boussinesq condition, the C1 gamma regularity is preserved. Gancedo and Garcia in another paper in 2D also consider the Cit0 consider the Cit0 be the characteristic function of D0, and they proved the C1 gamma, W2 infinity, and C2 gamma regularity are all preserved. Gancedo and Garcia also consider the 3D case, and they consider the more general temperature front initial data. That is Cit0 equals Cit star x times the characteristic function. Here, Cit star only defined on D0 bar. And under a critical Boussinesq condition, they can also show the global persistence results of the above persistent results are still hold. Here, note that the previous literature of both equations didn't address the case of CK gamma initial boundary for K strictly larger than or equal to 3. So my goal is consider this case. Let partial D0 belong to CK gamma. And we want to show the global CK gamma regularity propagation result of partial DT for 2D Boussinesq and 2D INS system. Besides, for 2D Boussinesq, we will consider the temperature patch of non-constant values. It usually called the temperature front, and it models an important physical scenario in geophysics. Here is the setting for these equations. The setting for 2D Boussinesq system, we consider the theta 0 be like this. It's a temperature front initial data. Here, D0 is a bounded, simply connected domain, and partial D0 belong to CK gamma. The setting for 2D INS system, the initial density is of such a patch data. Here, we only consider the at 1, at 2 are very close, and D0, the partial D0 will also belong to CK gamma, K larger than or equal to 3. For both equations, we both consider the level set characterization of D0. That is, there is a function phi 0. It belongs to the CK gamma. And the partial D0 can be expressed as phi 0 equals 0. That is, the boundary can be expressed as phi 0 equals 0. And the D0 can be expressed as phi 0 larger than 0. And graded phi 0 doesn't equal 0 on the boundary. Moreover, the boundary can be parameterized as following. There is a function z0, which is defined on S1 to the boundary. The partial alpha acting z0 equals the graded perp phi 0. That means the graded perp phi 0 on the boundary, in fact, is the tangential direction. And this we denote it as W0. Now we can introduce our main result. This is a result collaborate with Donghu Chai, which is from Korea, and Chen Yunmiao, which is from Beijing Institute of Technology, and myself. That theta 0 be the temperature front initial data, and the theta 0 bar belong to L infinity, and partial D0 belong to C1 gamma, and the U0 belong to H1, divergence free. Then there exists a unique global solution to the 2D Boussinesq system, and satisfy the following. The U satisfies these following estimates, and theta has the following expression, and partial dt belong to L infinity C1 gamma. If additionally, partial D0 belong to W2 infinity, and the theta 0 bar belong to C mu, and U0 belong to H1 cap W1P with some P strictly larger than 2, we can show the W2 infinity regularity is preserved. If partial D0 belong to CK gamma, and the theta 0 bar belong to CK minus 2 gamma, and the U0 also U0 satisfy this condition, we can show the CK gamma regularity is preserved. Here, the partial W0 U0 means the directional derivative of U0 along the vector field of W0. Here is a remark. Compared with the Gazzetto's result, we here consider the temperature patch problem of non-constant values, and we offer a simpler proof of the C1 gamma, W2 infinity, and C2 gamma regularity persistent result. Moreover, we also apply the stratified estimates method initiated by Sherman. And we introduce the stratified type Bezier space, the following stratified type Bezier space. Here is additional L index to measure the stratified level, which is defined as this. And we establish a series of stratified estimates in this space, and then we prove the CK gamma regularity persistent result. For the 2D IS system, we first recall the following C1 gamma regularity persistent result with any at 1, at 2 large 0. This is Gazzetto and Garcia's result. Let U0 be such a patch data, and U0 belong to H gamma plus S, divergence free. Then there exists a unique global solution to the 2D IS system. And the patch structure is preserved, and the boundary also belong to L infinity C1 gamma. However, for the 2D IS system, we didn't achieve the goal of showing the global CK gamma persistent result for any at 1, at 2 large 0. We just proved this, the following regularity result for at 1 is very close to at 2. This result is collaborated with my postdoctor Yatao Li. Under the assumptions of proposition 1, if additionally the initial boundary belong to CK gamma, and we have used the partial W0 to the power L acting U0 belong to C minus 1 gamma. And at 1, at 2 is very close. Then for any T and for any gamma prime belong to 0 to gamma, we have the partial DT belong to L infinity CK gamma prime. Here, if we can choose the evolved boundary is also very regular, but there is a arbitrary there is a very tiny regularity loss. If we replace the CK gamma with such a Bezier space, BK plus gamma infinity 1, it will be a regularity persistence result. Here's if additionally partial the boundary, initial boundary belong to the BK plus gamma infinity 1. And assuming that at 1, at 2 is very close, then the partial DT will belong to L infinity BK plus gamma infinity 1. Now, here is a remark on the theorem 2. The key point of Gancedo's paper, since they proved the persistence of C1 gamma, W2 infinity, and C2 gamma, the key point of his paper is mainly using the time-weighted energy estimates to step-by-step show the refined estimates of DTU. That is a material derivative of U. That is, they show the DTU has such a good estimate. One might expect to combine the procedure of Gancedo's paper with the stratified estimates method to show the CK gamma persistent result, but it will face some difficulty even at the first step. That is, in getting such a stratified estimate, stratified energy estimate, where the W is the graded perp of phi, and phi is the level set function of dt. Level set function of dt. W, if on the boundary, it's also W is the tangential direction. The main reason is that we need to treat the commutator term, this term. But in the proof, we only have the W belong to C1 gamma. We don't have, we only know that W belong to C1 gamma. We don't know, more regularity. It seems very hard to treat the term of this term in the energy type estimate, since we need this belong to L2. So this will belong to L2. But W only belong to C1 gamma, which will maybe there has some difficulty. Note that in Liao and Zhang's paper, due to the boundary belong to WKP, and Z can show that the W belong to L infinity W2P. And so the this term and other related terms can be controlled. So the time-weighted energy estimates combined with stratified estimates method can lead to the WKP persistence result for any at 1 at 2 large 0. But here for the CK gamma case, for any with any at 1 at 2 large 0, there we face much difficulty. And right now, I don't know how to overcome it. Now we talk about some proofs for the theorem 1, which on the 2D Boussinesq system. In order to prove the C1 gamma, W2 infinity, C2 gamma regularity persistent result, noting that the domain dt has the level set expression phi t, which solves the following equation. It's a transport equation, and initially it is phi 0. We mentioned before. And one needs to prove uniform boundedness of phi t in C1 gamma, W2 infinity, and C2 gamma. A new ingredient is the introduction of a good unknown. Here is denoted as gamma equals omega minus R minus 1 actin theta. Here omega is the vorticity, and R minus 1 is an operator of -1 order. Such a quantity, in fact, is widely used in 2D Boussinesq system with partial fractional dissipation. One can see Hamidi, Kareni, and Rossetti's paper. Here is the derivation of this quantity is very simple. Note that the equation of vorticity is the following. And so if we put the partial one seat on the left hand, it will become this equation. And also the equation for r minus 1 seat is the following. If we subtract these two equations, which will lead to this equation of gamma. If we compare the equation of gamma and the equation of omega, we see the forcing term. Forcing term in gamma equation is much better since it's a commutative term. The gradient can be transferred to u from the theta. So this equation, the gamma equation is much better than the omega equation. In fact, by using the commutator estimates, the quantity gamma usually has very good regularity estimates. So if we want to control the gradient, control the velocity, then the gradient u can be splitted as the following two terms. One is a gamma term, and the other is a theta term. The gamma term usually has good control. And then for the theta term, since theta is belong to L2, L infinity, L2 cap L infinity, and the operator in front of theta is an operator of -1 order. So we can directly prove that gradient u belong to L1 C gamma. Moreover, the particle trajectory will belong to L infinity C1 gamma, which ensures the phi t belong to L infinity C1 gamma. Now, for the W2 infinity result, the main task is to show the U belong to L1 W2 infinity. Since it will imply the uniform W2 infinity boundedness of phi t. And from the relation, above relation, we mainly need to show that the theta term belong to L infinity, L infinity. Here, theta has the following expression. The operator in front of theta, in fact, is a singular integral operator. In general, it doesn't belong. It acting a L infinity function doesn't belong to L infinity function. But here, the theta has the patch structure. It may have the patch structure maybe introduce some advantage. The situation here is quite analogous to that in the vorticity patch problem of 2D Euler equations, where we need to show that the gradient u, which is related with omega as this, it belongs to L infinity. Here, omega is of the patch structure. So we here adopt the Bertozzi and Constantine's method, especially the geometric lemma, we can indeed show that the above the C term belong to L infinity, L infinity. Note that here, in fact, the temperature patch problem is much regular than the vorticity patch problem, since here we only prove the U belongs to W1 infinity, but here we can prove the U belong to the W2 infinity. It has one derivative advantage. And then now for the C2 gamma persistent result, we now consider the W. W means W, especially on the boundary, that's the tangential direction. W will satisfy this equation, by asking the C gamma norm of graded W. It mainly needs to show the partial W of graded U belong to L1 C gamma. We also use the above relation when we need to consider the gamma term and the theta term. For the gamma term, note that the partial W gamma will satisfy this equation by using the product estimate. We can use the smoothing effect of Hart equation to get the following estimate. And then combined with the following stratified estimate, the following stratified estimate, we can now control the gamma term. Gamma term has the following estimate. And for the theta term, similarly, we can consider have the following estimate. We need to consider the red term, the partial W acting theta. We have note that partial W theta has satisfied this equation. This equation is a transport equation. So we easily get the B gamma minus 1 infinity estimate. And we want to see the partial W0 acting theta 0. It indeed belongs to the B gamma minus 1 infinity. This can be shown this the following lemma. If partial the initial boundary belong to CK gamma, and the theta 0 is the temperature fronted initial data, and the theta 0 bar belong to CK minus 2 gamma, then we have this estimate. Note that if theta 0 be only the characteristic function, the partial W0 acting the 1D0, in fact it is equals to 0, since the D0 on the boundary is the tangential direction. And for more general data, we can also show this estimate. So therefore, we can get gathering the above estimate, we get this estimate. the groundwork inequality will finally get this estimate, which means now we can control the W belong to L infinity, B gamma plus 1 infinity infinity. Now, in the proof of propagation of higher CK gamma boundary regularity, motivated by the Schemann's paper and Liao Zhang's paper, it suffices to show the stratified estimate of following stratified estimate. The partial W to the power K minus 1 acting W belong to L infinity C gamma. And the method of stratified estimates initiated by Schemann plays an important role. However, we want to point the regularity of vector field W and its stratified counterpart in Schemann's paper are of the C gamma type. Gamma is of harder regularity, but in our situation, they all belong to the C1 gamma. It's much regular. As a consequence, it yields substantial difference in analysis. The foremost one is the estimation of RQ, which will appear in the analysis. Here, Fi has some flare support on a ball with radius of Ci to Q. In fact, the Schemann's paper, it have such a estimate in lemma 1. The operator, the T W dot graded means the classical power product operator. To the power L acting RQ, it has such an estimate. There is a factor, the blue factor. Since the blue factor, such a factor will lead to stratified estimates with in Schemann's paper and Liao Zhang's paper with essential epsilon regularity loss. But in our case, there will be no regularity loss. So we introduce such a stratified type Bezier space, BSL-PRW, is as following. If P equals infinity, we use the following abbreviations. The following that BSLW means the BSL infinity 1 W. Since there will be no regularity loss. In fact, we can prove the lemma 4. Using the power differential calculus, we can establish some refined stratified estimates. If W be a divergence-free vector field, satisfy this condition, that the stratified index is chi minus 1, and MD is 0 order, and U is divergence-free and smooth, phi is smooth. For every epsilon belong to 0 to 1, there exists C depending on this norm, stratified norm of W, such that we have the following stratified estimates. The U dot graded phi of this stratified norm have bounded by the right-hand side. The minus epsilon, the regular index can either be with graded phi or be with U. it's all okay. And for MD operator acting phi, the stratified norm can be has the following bound, and also the commutator estimate. These stratified estimates are natural generalization of some classical product and commutator estimates in the Euro-Bezoff space with negative regularity index, which might be interesting in its own. Now we turn to the CK gamma persistence result. We use the induction method. The goal is to show the partial W to the power k minus 1 W belong to L infinity C gamma. In fact, we will prove the following estimate. Suppose for L belong to 1 to k minus 2, the 14 holds. We tend to show the corresponding estimates with L plus 1. Note that the C2 gamma persistence result correspond to the 14 with L equal to 1. So the procedure is as in proof of C2 gamma persistence result. In order to get the stratified estimate of W, we consider the L infinity B gamma minus 1 infinity norm of this quantity. By using its equation, we get this formula. Using the stratified estimates, we can get the following estimate. That is, we mainly need to consider the stratified estimate of the U. We also use the relation. We treat the gamma term and the seed term separately. For the seed term, by using the stratified estimates, we have this bound. And the stratified is from the equation of partial gamma to the power I acting theta, we can get this estimate. Finally, the seed term is under control. For the gamma term, we also use the stratified estimates. And we have this bound. We need to control the term in blue. Consider the smoothing estimate of the partial W to the power L plus 1 gamma. From its equation, and using the stratified estimates, we finally can arrive at this estimate. Gathering all the above estimates, we can finally get the following estimates. And now we can use the groundwork inequality and also the induction assumption, which will guarantee the desired result. I think my time is over, so I think I will stop here. I skip the proof for the IS system. Thanks for your attention.
Okay, thank you for your nice talk. So now, time is for question or comment. Do you have any question or comment? Okay, so I have one question about INS.
Okay.
So you assume that the eta 1 and eta 2 is very close, right?
Yes.
So why do you need such a condition?
Since in Ganseto's paper, they don't need such a assumption. But here we want to extend their method. I'd want to combine their method with the stratified estimates method, but I face some difficulty. This I make some explanation here in this remark. We even at the first step, we will face some difficulty. So I didn't use their method. So I just you can see here. I mainly put this term as a error term. Put it on the right hand side. If at one is very close, one, it can be observed by the left hand side. I didn't use Gancedo's method since I face some difficulty. Right now, I don't know how to overcome it.
Okay, thank you. And okay.
Maybe it's a technical problem, but I don't know how to overcome it.
Okay, thank you. And for me, this is very close to the two-phase free boundary. There is some relation between this patch problem for INS and the two-phase free boundary. Do you have another representation, for example?
I don't know. I don't know much about the two-phase problem. I'm sorry, I can't give you more information. Yeah, that's a very interesting problem. Maybe I will see the two-phase problem to know more, to see the relation with the patch problem of IIS system.
Oh, okay.
That's a very good problem.
Okay, thank you.
Yeah.
Do you have other questions or comment? Okay, if not, let's thank speaker again. Thank you. Very interesting talk. Yes.
Yeah. Thank you very much.